Welcome back to Differential Calculus. In this video, I want to talk a little bit about absolute value. You've almost certainly worked with absolute value in a previous course, college algebra, pre-calculus, elementary functions, whatever it happened to have been named. But my experience is that absolute value is one of those concepts that all too often gets glossed over at that level. And it's one of the foundation of ideas that builds to calculus as we talk about it today. And so before we get much further, I really want to go back and make sure that everyone has a firm understanding of absolute value, starting with the definition. So let me get my head out of the way. The absolute value of a number x in the real numbers. All right, so we are specifying here early in the definition. We want to be able to take any real number and define absolute value. And another common phrasing in vocabulary in definitions in mathematics is denoted and defined. We are going to set up the notation of absolute value, the one that you're familiar with, the vertical bar on the left and right of the number. And then we're going to put an equal sign, and to the right of the equal sign, we're going to give the definition of absolute value. Sometimes you'll see separately slightly different looking equal sign to mean defined. The phrasing is denoted and defined. It tells us that that's what we're using this for. We don't have to go into any of that. But absolute value is defined piecewise. Absolute value of x is defined as x if x is greater than or equal to 0. Absolute value of x is defined as the opposite of x if x is less than 0. And if you've not seen this definition, you're probably stopping and scratching your head because you know that absolute value is supposed to take any number and turn it into a positive number. And that's not what this definition seems like at first. But if you stop and think about it, that is what it's doing. If I take a positive number, say 7, and I want to take the absolute value of 7, well, following the path here, 7 is greater than or equal to 0. And so I should return back the number that I gave it. The absolute value of 7 is 7. If I put in 0, I know that the absolute value of 0 is 0. And if I follow my path, when x is 0, it is true that x is greater than or equal to 0. And so it returns x, which was 0 in this case. And if I try something like -3, well, here, when x is -3, that means that x is less than 0. And I want to return the opposite of x. So I want to return the opposite of -3, and the opposite of a negative number is positive. So yes, this definition of absolute value does exactly what you think it's supposed to do. If the number is positive, it leaves it alone. If the number is 0, it's still 0. If it's negative, it turns it positive. This is mathematically how we can define if it's negative, turn it positive. When I think about absolute value, the application that I see most frequently is distance in one dimension. If I'm able to draw a number line and I'm able to spot 2 points, x and y on the number line, it is clear with how I've drawn this that x is the smaller number and y is the bigger number. right? Number lines always have smaller numbers to the left and larger numbers to the right. And so the distance between x and y is y minus x. We know that's the order we want to put it. Larger number minus smaller number. But what if we didn't know? If I don't know anything about real numbers a and b, but I want to calculate the distance between them. I know that the distance between these numbers should be positive. A negative distance doesn't make sense. Anyone taking physics, there is a distinction between distance and displacement. A negative displacement can make sense, but that's not a distance. A negative distance cannot make sense. So we do our subtraction. Is it a minus b? Is it b minus a? I don't know. I'm just going to pick one. But whatever that number is, I want to make sure it's positive. To make sure it's positive, I surround it with absolute value bars. Right? So if b is bigger than a, you do the subtraction, it's positive, absolute value does nothing. If b is the smaller number and a is the larger number, then when you do the subtraction, it's negative, and the absolute value takes the negative number and turns it positive. So your distance is always a positive number. If you think that distance being a negative number makes sense, see if you can find me a table that's negative 5 feet wide. I've been offering for a couple of years this. If anyone can find a table that's negative 5 feet wide, I can probably get you a $1 million prize, 10% finder's fee. So we have our distance, we know it's a positive number, and more importantly, this is the context in which absolute value is discussed. When you see absolute value in calculus, think of distance, the distance between A and B. And when we're thinking about distance, we can start thinking about some really interesting ideas. One of my favorite ideas in mathematics, because of how obvious it is, and at the same time, how not obvious it is, how many places it comes up that have nothing to do with triangles, but the triangle inequality. No side of any triangle can be longer than the sum of the lengths of the remaining sides. Well, obviously, if you draw a triangle and you start with two relatively short sides of the triangle, and then you draw a very long side of the triangle, well, they don't meet. You cannot choose an angle to get those sides of the triangle to meet. But this works no matter how you phrase the distance. So the length of a side of a triangle is the distance between 2 points. And okay, one-dimensional triangles aren't really a thing, but let's just roll with it. If you've got one side of the triangle, the distance between the two ends of the triangle has some length, we'll call that the absolute value of A. A second side of the triangle has some length, we'll call that the absolute value of B. And again, whenever you see absolute value, you're thinking a distance. And the third side cannot be longer than the sum of the remaining two sides. So that means that if I take these two sides and add them together, it has to be greater than or equal to what I would get if I put those two sides together and got the whole distance before taking the absolute value. Throwing in some positive numbers, say A is 2 and B is 5, we get 7. And if I try it in the other order, 2 plus 5 is 7, and the absolute value of 7 is 7. That works fine. If I choose a positive and a negative number, -3 and 4. Well, the absolute value of -3 is 3, the absolute value of 4 is 4, 3 plus 4 is 7. Or on the other side, -3 plus 4 is 1, and the absolute value of 1 is 1. It's not the same, but the relationship we're looking for is greater than or equal, and greater than or equal is still satisfied. This idea of the triangle inequality will come up a couple more times this semester. For right now, the big idea I'm looking for is having it start to make sense. When you see absolute value, you're talking about a distance in one dimension. Right? Again, if a one-dimensional triangle doesn't make sense to you, that's okay. It doesn't make sense to me either. But this idea of take two sides and bring them together, and then take the length of those sides and try to figure out what's happening. You can't make a total trip that goes further than the distance you travel in each leg of the trip. All right. All of that out of the way, it's time to start solving some absolute value equations. So let's say that we have the absolute value of 3x plus 4 equals 7. I don't know whether 3x plus 4 is positive or negative. And depending on which of those is the case, changes what happens here. If 3x plus 4 is greater than or equal to 0, then the absolute value of 3x plus 4 is 3x plus 4. And I get that the solution is x equals 1. But if 3x plus 4 is less than 0, then the absolute value of 3x plus 4 is the opposite of 3x plus 4. And I get that x is negative 11 thirds. Well, I don't know. I can double check. If x is 1, right? If I try the x equals 1 case, all right, 3 times 1 plus 4 is 7. That's definitely greater than or equal to 0. So it satisfies the condition we had. I can check the negative 11 thirds case. If I put that in up here, 3 times negative 11 over 3 is negative 11. Plus 4 is negative 7, which is definitely less than 0. So that satisfies that condition. Both of these are perfectly valid. And so sometimes you will see, especially in algebra or very abstract calculus, when a situation like this comes up, we will collect our results and put them together in a solution set. If I had more context, it might be the case that only one of these actually solved the problem, but I don't have more context. Right? It could be that the solution that makes sense, that is useful to us, is x equals 1. It could be that the solution is x equals negative 11 thirds. I don't know. The idea of a solution set, the thing that we're looking at here, is that both 1 and negative 11 thirds solve the equation. They both satisfy the equation. And there is nothing else other than these 2 points that satisfy the equation. Right? So when we talk about solution sets, that's the shorthand we're using. Everything in the set is a solution to the equation, and there is nothing in the set, or there's nothing that satisfies the equation that is not in the set. I'm not going to write that vocabulary down. It's not that important. But you will see some problems asking you to play around with that, including the one coming up right now. I would like you to find the solution set for the absolute value equation, absolute value of 4 minus 5x is equal to 12. All right, take a couple of minutes, see what you can do with that, and I'll see you in the next video.